In my hand right now, I'm carrying what's called a dosimeter, and it's a tool for measuring radiation. Why do I need a dosimeter? Well, although there shouldn't be any significant radiation where we're about to go, there could be, because we're here at TRIUMF, the particle acceleration laboratory here in British Columbia, Canada, that houses the world's largest cyclotron and, soon, the world's most powerful linear electron accelerator of its kind. And what do they do here? Oh, just casual things, you know, like advancing the fields of physics, medicine, material science, and much, much more. So, without further ado, let's head inside and talk about how they accelerate particles to about 75% of the speed of light, and also why the heck you would want to do that in the first place.
Storyblocks Video offers you studio quality stock video clips for a fraction of the cost. Check it out today at the link in the video description.
When you think particle accelerator, the first thing that probably comes to your mind is CERN. They are famous for digging this great big tunnel that allows them to accelerate two beams of particles to near the speed of light, then smash those two beams together and see what happens. Well, TRIUMF is a little bit different. They are more about directing a single beam of super fast particles at an object like, say, a piece of uranium. By doing this, they can achieve a couple of things. One, they can create isotopes or forms of elements and compounds that generally don't exist naturally. Fluorodeoxyglucose, for example, is used for brain research in the nearby University of British Columbia. Or two, to actually produce elements that either wouldn't naturally occur or that would be very difficult to study inside the neutron-star merger you'd have to travel to in order to find them. Before we get into that though, let's go all the way to the beginning with this rather unassuming bottle of compressed hydrogen. So the hydrogen gets sucked up through this tube right here, all the way up to this spot right here. And then this chamber, this whole thing, is kept under a vacuum, so that takes care of the pumping. Then it comes down into this plasma bucket, which is right here, where a 2000 degrees Celsius tantalum filament ignites the plasma, strips the electrons from the atoms, and then the hydrogen anions. So these are the hydrogen atoms that pick up extra electrons, are fired out through here, and like really fast, because our 12,000 volts here is not compared to ground, but rather to the entire source room that we're inside, which is kept at 300,000 volts compared to ground when the accelerator is running. It's a good thing it's not on. Now we're on the outside. So directly above me is where our hydrogen anions leave the source room. So from this room to the wall here are a bunch of linear resistors. So the potential then goes smoothly from the room up to 300,000 volts at the wall. And when the particles leave here, they'll be traveling at roughly 1/40th the speed of light. To put that in context, that's about 160,000 times faster than the top speed of my car. Now, dealing with a huge electric potential like this isn't easy. While our power supply here isn't actually working as hard as you'd think, it only uses about 1 milliamp once charged to maintain that potential. If given the chance, it will gladly create a literal bolt of lightning between the room here and the wall. So, to prevent this, they've had to do a couple of things. First of all, this entire room is a Faraday cage, and no wires can go between it and the wall, or it'll be Spark City in here. So all of the data and the control signals are sent over fiber optic cables, which is pretty standard. But then what about power? You can't do fiber optic power. Well, that is where this comes in. So rather than just running a wire, remember, we can't do that or bzzzt, they ran this non-conductive shaft with a 30 horsepower motor on the other side of the wall that allows them to convert mechanical energy here into electrical energy, just like a bog standard generator. Pretty clever. Now we're above the particle accelerator, where our wicked fast anions are coming shooting down this tube. But we have a problem. Since they don't just come out in a nice orderly fashion like a laser, but rather tend to scatter like a flashlight, the main goal here is just getting the particles down there, which requires some real, particle wrangling. And all along this line is TRIUMF's sort of H- particle prod of choice. Basically, they're precision manufactured electrostatic plates called quadrupoles that act kind of like lenses for the charged particles to keep them in line. And the same technique gets used right here, where the particle beam actually gets turned before being sent one floor down into the real meat of the particle accelerator, the 520 mega electron volt cyclotron, the largest in the world. So before we go inside, there's a few things that we've got to do. Any contamination on the surfaces inside the cyclotron will need to be cleaned after we leave. So they've asked us to wear lab coats so we don't shed any unnecessary dust, and also to wear booties and not kneel down on the floor or anything like that, just to create as little extra work as possible for all the techs that keep this place running smoothly. This is a very high technology contamination control barrier here. I like it. Okay, now we are getting into where the magic happens. The cyclotron, and sorry, getting a nasty look here. Sorry, not magic, science. Magic isn't real, science is. Anyway, at this point, our H- particles are entering the circular track at 1/40th the speed of light, where large RF resonators provide the acceleration and massive deionized water-cooled coils of aluminum hold the particle on orbit. Now there are two coils, both with 15 turns positioned around the cyclotron, and each one carries 18,000 amps. But that incredible power doesn't mean that the researchers here don't also have a fair degree of control over the speed of our particles. So as they whip around the loop, the H- particles will go faster and faster. It actually takes about 1,600 laps before they'll reach full speed. That's about 3/4 of the speed of light. But what they'll also do is a kind of spiral outward, taking a wider path around the accelerator. Kind of like how in your car, if you're going faster, it's hard to take a tight turn. That means that when it's time to apply the last step, using a thin piece of carbon foil to strip the electrons off so that we're left with just bare protons, the energy of our protons can be fine-tuned according to where the carbon is positioned. On the inside of the cyclotron gives us slower, lower energy particles, or right out at the edge of the cyclotron gives us the full 520 mega electron volt experience. Once the electrons are stripped, our coils will no longer keep the stream going around the track, so we're left with a straight stream of positively charged particles that'll turn whatever poor sample is on the other side into matter soup. Of course, you can't have those particles smashing into anything unintentionally, like air, so the entire cyclotron needs to be held at a vacuum of 0.0000000001 bar. To accomplish this, they use, this sounds so cool, turbomolecular pumps that spin at 40,000 RPM, basically like smacking the air molecules out and not allowing them back in. Now, this does create the small problem of making the vacuum chamber, which is above us, want to collapse in on itself. However, to combat that, we're actually currently below the cyclotron, do you see all these poles here? Well, you might actually think that these are supporting the cyclotron, like struts or something, but they're actually pulling down really hard to make sure the whole thing doesn't just flatten itself. So that was pretty sweet. But just like you guys will occasionally get the itch to upgrade a graphics card even if you don't really need to, but you just want the latest and greatest, well, after 45 years of operation, eventually the thrill of shooting protons at 3/4 the speed of light around the cyclotron started to wear off a little, and the researchers at TRIUMF needed a new way to smack stuff together at super high speeds and continue to push the frontiers of understanding. So they built the world's most powerful electron linear accelerator, or ELINAC. So when it reaches full power in 2025, the ELINAC here will be able to propel 100 kilowatts of electrons at a blistering 99.99% the speed of light. Wow. So to accomplish this, they first need yet another 300 kilovolt power supply in a Faraday cage of it. What is it with these guys and their 300,000 volt power supplies and Faraday cages? It's like a nice round number or something. Anyway, that gives the electrons a pretty nice kick in the butt to roughly 77% the speed of light. But that's just too slow. That's like peasant stuff. Where they really start cooking are in these radio frequency wave chambers. So the insides of these are cooled down to just 2 Kelvin using liquid helium surrounded by a liquid nitrogen cooled heat shield. I guess that's why they call it the super thermos. And in there, the electrons are accelerated by the radio frequency field in here oscillating rapidly, 1.3 billion times per second, with these oscillations synchronized to the speed of the electron going through it. So what that means effectively is that the electron is always being pushed along to the next segment, kind of like a railgun. Now, one of these accelerators would get our electrons up to 10 mega electron volts, but that wasn't enough for them. So they got 3. 3 in a row gives it a total of 30 mega electron volts of particle smashing power. So all in all, this accelerator consumes 1 million watts? Watts. Or about enough power for 1,000 homes. All right, so we've had a lot of talk so far about particles going at obscene speeds. But now it's time to transfer all of that momentum into something useful. Now, depending on the experiment, what happens next can vary a lot. But normally it consists of getting the beam to a point where it smashes into samples of materials called targets, where the particles have enough energy to split the nucleus of the atoms. This can create all kinds of fun things. Neutrons, muons, or rare isotopes via nuclear fission or spallation. And it also creates a big old pile of matter garbage. So, at risk of sounding like a broken record here, this is where things get tricky, because you might not have a lot of time to grab the important bits. Some of the rare isotopes that they want to study might only last for a few milliseconds before decaying. So, nanomaterials are designed and brought to temperatures white hot, around 2,000 degrees Celsius, to release the isotopes super fast. Then, depending on what exactly is smacked together, some of the longer-lived isotopes might get collected locally, while other particles would need to go through several switching stations, some of which are below us here, or, for further acceleration, to arrive at an experimental detector. The one behind me here, called the Titan ion trap, accurately measures an isotope's mass using its cyclotron frequency. So basically, there's a combination of magnetic and electrical fields that trap the particle in a confined space, and then you can calculate how fast the particle moves around a track, and from there, calculate its mass. Alternately, your isotope might get switched off of the main line over there and end up in something like Griffin, which is kind of like a microscope that's looking for nuclei. So Griffin is actually the world's most powerful tool for the decay spectroscopy of rare isotopes, and it provides TRIUMF scientists with an unparalleled view of the interplay of forces that create nuclear structure. Here on the other side, the isotope atoms are delivered into the black ball that it was showing when we were here for B-roll, so we can show it to you, but I can't point at it now. And then they're deposited on a tape reel. And as they decay, gamma rays are emitted and then are measured by these detectors that go completely around the sample, giving a full 360 degrees of detection. After the measurement is performed, the tape reel gets spun, some of which have decayed into daughter nuclei that create unwanted gamma ray background noise, come out through the lead wall on the other side, which shields the detectors from the daughters. More isotopes can then be deposited on the tape, and it's good for another go. These isotopes are used to help us understand fundamental physics, but there are also lots of other applications. Isotopes created here at TRIUMF have been used for things like tracking the movement of plankton, detecting brain disease or cancer, treating cancer, characterizing candidate materials for superconductors, understanding how metal ions make proteins and enzymes in our body do what they do, and you know what, honestly, if I were to list it all in this video, we'd go on for another 10 or 20 minutes. But Linus, I'm sure you've been screaming at the screen for the last 10 minutes or so. When are you getting to the cool computers? Okay, now. So behind these doors is a Tier 1 data center that analyzes experiment data from the ATLAS particle detector at the Large Hadron Collider. It has a 100 gigabit fiber pipe capacity that connects to the LHC over at CERN in Switzerland and other sites around the world so that they can share the ridiculous amount of computing and storage needed to analyze and store the massive amounts of data that ATLAS produces. So in there, they've got 12,500 CPU cores, 12 petabytes of disk storage, and 31 petabytes of tape storage. Oh, it does open, but I thought it was gonna be locked. Unfortunately, we're not actually allowed to go in there. Something, currently holding the record for Tier 1 computing uptime, something, me getting close to it, I don't know. I don't really know what the issue was. So this was really cool, and it's the end of our tour, but it's hardly the end for the work being done here at TRIUMF. They're actually expanding like crazy. Along with ramping up the ELINAC, they're gonna be tripling their rare isotope production capabilities in the next couple of years, adding another building and continuing to employ around 100 co-op students every year to teach them about particle acceleration. So maybe then we'll have to come back when they've got another big update to show us. Maybe we can get behind those data center doors next time. But in the meantime, I just want to give a huge shout out to Stu for coordinating our tour and to the legion of experts that showed us around. It was a lot of fun to get to spend a day with what are probably some of the smartest people here in Canada.
Get studio quality stock video clips for a fraction of the cost with Storyblocks Video. Download all the stock video your heart desires from their member library, including HD and 4K footage, After Effects templates, motion backgrounds, and more. We actually use it here quite a bit for Tech Quickie. Plus, get exclusive discounts on millions of additional marketplace clips, and the original artists take home a commission of the sale price. All content is royalty-free, so you can use it for commercial and personal projects, such as YouTube videos. New clips are added regularly as well, so there's always something fresh to download. Check it out today at the link below to learn more.
So thanks for watching, guys. If you disliked this video, you know where that button is. But if you liked it, hit like, get subscribed, or maybe consider checking out where to buy the stuff we featured at the link in the video description. But I hope you've got like $1 billion if you want one of these, because like probably more than that. Yeah, I'm getting the nod. More than $1 billion. Anyway, also linked in the video description is our merch store, which has cool shirts, not this one, but like this one, and our community forum, which you should totally join.